So I hope everyone had enough cheese to keep you alert for the talk. I think I certainly had enough to keep me alert for giving the presentation. So before picking up where we left off yesterday, I wanted to say that there's an excellent reference. So if you're interested after these couple of lectures, if you want to learn more, or if you just want to find all the mistakes in what I've been saying, there's a book, The Algorithmic Foundations of Differential Privacy. And actually the whole book is available for free online, so there's a PDF on Aaron's webpage, and I highly recommend it. It's a great book. So let's recap where we were yesterday. We were discussing the quest for privacy-preserving data analysis, for getting privacy together with utility, and I want to recap a little bit the definition of differential privacy, and we'll see with a little bit of a twist that will be helpful for the lecture today as we go on to more sophisticated algorithms and techniques. So remember the definition of epsilon differential privacy. For every two databases, D and D prime, that only differ on one person's presence or absence. So this is, remember we had the D plus me and D without me. This is D and D prime. And for any event that can happen, as we said in the lecture yesterday, and I'm sure everyone remembers, it's enough when we're talking about differential privacy to talk about singletons, about single outputs. So for any output in the range of an algorithm, we say that the algorithm A is epsilon differentially private if the ratio of probabilities, the probability that running on the database with my data and the data set without my data, the probability that we get outcome C are about the same. In particular, the ratio is between e to the epsilon and e to the minus epsilon, so the log of the ratio is between minus epsilon and epsilon. It's very small.
What happens to the query?
So A is an algorithm, and supposedly it's answering a collection of queries, but who knows what it's doing. Maybe it's doing some regression, maybe it's doing sophisticated analysis.
For every query.
This is for an algorithm, and we're separating it from utility. So this is a definition of privacy, and there's a question of utility and what exactly the algorithm is supposed to accomplish to better, the future of the world and humanity. But this is just a definition of privacy. Okay, and then we had the definition of epsilon, the relaxation, the epsilon delta differential privacy, and I want to present an equivalent but slightly different formulation from what I told you yesterday. Mm-hmm. Why do we think of the event of being bad? Well, that's just intuition for why that guarantees that I'm protected from harm. So for any bad event that could happen to me when I'm in the data set, it could happen with about the same probability when I wasn't in the data set at all. Presumably bad privacy events don't happen when I'm not in the data set, so this is giving good privacy protection. Okay, so that's just a recap from yesterday. Epsilon delta differential privacy, the way I'll present it now is slightly different, or the formalization will be slightly different. So what we say for epsilon delta differential privacy is now for any two adjacent data sets, so again, this is with my data, this is without my data, with very high, with all but negligible probability over the coins of the algorithm A, sorry, this should be a D, not an X. So with all but delta probability over the coins of the algorithm A, when we run it on the data set D, when we look at the outcome, it was just as likely, or it was almost as likely, if we were to run the algorithm on data set D prime. Okay, so think about it this way. When we get an outcome C for which this ratio holds, an adversary can't quite tell whether we ran the algorithm on data set D or data set D prime. It looks about the same. It's about equally likely. And that's a good situation. That means privacy is preserved, and this definition or this formulation is making it explicit that with all but a negligible, think of this as an exponentially small probability of error delta, privacy error delta, this ratio is small. It's between, the log ratio is between minus epsilon, and so privacy is preserved.
Sorry, what is random inside
the algorithm? So the algorithm A is a randomized algorithm.
Yeah, but then you take the probability in the ratio, so...
That's the probability over A's coins. So A is the only randomized thing in this. So the probability of the outcome, so I got a certain outcome. Suppose the outcome has probability 1 over n when I run the algorithm A. It should have about the same probability 1 over n if I ran the algorithm A on database D prime.
Yeah, so what is X then?
X is a mistake. X should be D. So that's just a typo. When I run the algorithm A on the data set D, I get the outcome C. And this outcome should have about the same probability according to, say, the data set D or D prime. So let me...
D and D prime are not symmetric here.
They're not symmetric. Absolutely, that's right. They're not symmetric, what you're saying, and you're absolutely correct in the sense that we're generating the outcome by running the algorithm A on data set D.
But in yesterday's definition, it was symmetric.
So it was hidden. They are symmetric because it's required to hold for all D and D prime, so you could flip the roles of D and D prime, and then the definition still needs to hold. So the guarantee is symmetric, but the way I presented the definition here, the formalization, I'm fixing first D and D prime, and I'm running the algorithm on data set D to produce the outcome. And the two definitions, the one that I showed you yesterday, where you are allowed to add or subtract a delta additive quantity, these two definitions can be shown to be equivalent. It's actually a non-trivial proof, but they can be shown to be equivalent. But this formalization will be helpful for what we do today, so please keep asking me questions if you have them.
Yeah, I'm sorry, there's still something I don't get.
Mm-hmm.
So you take the probability that your algorithm outputs something.
Mm-hmm.
So since you upgraded the randomization of the algorithm, then your probability is a deterministic quantity. So the
Yes.
log ratio is deterministic. So how can you say that with a high probability?
So again, once we fix C, I agree with you. Once we fix C, the outcome, this is a number. The probability that the algorithm outputs C is just a number. It's a real value between 0 and 1. The probability that the algorithm on data set D prime outputs C is also just a number between 0 and 1. So this log ratio is also, hopefully it's defined, so the denominator isn't 0, and this log ratio is a well-defined number. Everything is well-defined. Once you fix C, the probability is over the choice of C when we run the algorithm A. Yeah. It's a good question. Yeah. Okay, and what I really want to make explicit in this formalization, and the reason I wanted to present it this way, is that really we can look at this quantity that we refer to as privacy loss, or the privacy harm that's happening to an individual, as a random variable over the coins of the algorithm. So fixing two adjacent data sets as we did, D and D prime, we can draw the outcome C, we can run the algorithm A on D, we get some outcome C, and we can define the privacy loss on this outcome as the log ratio of the probabilities that we get this outcome according to D and D prime, and intuitively that's a quantitative measure of the privacy loss that's been incurred by running the algorithm A and seeing the output C. It captures somehow the confidence or the information, at least in an intuitive level, it captures the information that an adversary learns from seeing C, or the advantage it now has in distinguishing whether I was in the data set or not in the data set.
So is this loss connectable to other notions of mutual information or something like that?
So we'll see that it's, so what we'll use today is we'll actually make it explicit and use a connection to KL divergence. So maybe I'll answer it within this slide, and I'll give you. Mm-hmm.
Does the composition you showed yesterday also hold some manner on delta? What happens to the delta?
It does. The deltas add up. Yeah. Yeah. I won't talk about it.
Sorry, one more question.
Mm-hmm. Oh, but I think questions are good, so the more the merrier, especially after all the cheese.
Can you just put, so this is some measure of distance between distributions. And why is this the right measure? Or did you talk about that last time? Or can we use L1 distance?
So L1 distance between there are many measures, and I think some of them make sense and some of them don't. This measure has some unique advantages in that it, for example, composes. Statistical distance also composes, but the problem with statistical distance is if we run, so we talked about it yesterday, if we pick a random victim in the data set and publish their information, then the distance between the two distributions is just going to be 1 over n, the number of people, the probability that, say, I was selected. That's a very small statistical distance. But for privacy, this is a terrible idea. So, however, for example, if you insisted that the statistical distance be, so you can't have, and statistical distance is a little problematic. Because of hybrid arguments, you can't have sub-polynomial statistical distance. If you want, the answers on two data sets that are distance n from each other to be very different, which you do, then you can't have the distance between any two adjacent databases be more than 1 over n, so it's a problematic measure to work with. But you could think about lots of, you could think about things like KL divergence, you could think about different measures of distances between distributions. It's insufficient, but we'll use it today. We'll see that for some things it does give you some guarantee that's actually helpful. So actually, why don't we just make that explicit? So this privacy loss, when we fix our adjacent data sets D and D prime that we're worried about, the privacy loss that we get is a number. This is a number. We draw C and we get some number that quantifies the privacy loss. This is an advantage of differential privacy. It actually lets you quantify what happened. And this number is a random variable. The random variable is over the choice of C. Okay, that's going back to your question. So in particular, it's a random variable. That means, it's a real valued random variable. We can try to reason about it. So it has a mean, it has a variance, and we can use these things, yeah.
Do you mean here the absolute value of this?
No.
No?
And that's important.
But what does it mean? That if it is negative, then there is no privacy.
We will make a very good use of that. So think, for example, so this value can be negative. The definition requires that its magnitude is bounded. So it's between minus epsilon and epsilon. Its magnitude is bounded by epsilon. But it can be negative, and intuitively, this makes sense. So think, for example, that we're running an analysis now to see how many people in this room are above 6 feet tall. Okay? I'm above 6 feet tall, and I'm worried about my privacy. What we do is we count the number of people, and we add some noise to it. And we release this noisy statistic. If the noise is positive, then it makes it sort of more likely that I was in the room. Okay? An adversary by seeing the output, the adversary will think, oh, Guy was probably in the room. But if I was lucky and the noise came out negative, it makes it look less likely that I'm in the room. So in some intuitive sense, I've had negative privacy loss or privacy gain. And we can actually leverage this. It'll play a big role in one of the theorems that I'll talk about today. So we can think about privacy loss as a random variable. It has a mean. In particular, the mean is the KL divergence between these two distributions. Okay? So that's very nice. So hopefully it will have small mean. It's insufficient. So so that's helpful, and we'll think about means, but we also want to bound more than the mean. We want to bound things like the variances and the higher moments. So thinking about privacy loss as a random variable, we can now come back to the definitions we talk about. Epsilon or epsilon 0 differential privacy says that with probability 1, always, no matter what coins the algorithm tosses, probability 1 over the choice of C, the privacy loss has magnitude at most epsilon. Okay, we're simply restating what it means to be epsilon differentially private. Epsilon delta simply says that with probability 1 minus delta over the coin tosses and the choice of C, the privacy loss is at most epsilon. So there's some delta probability of error, but otherwise we have magnitude at most epsilon. So we'll make a digression and come back to it. I wanted to make a quick pointer. So since there has been interest and we've been talking about relaxed notions of privacy, and I think this could be interesting for the audience, I have some recent work with Cynthia Dwork where we define a relaxation called concentrated differential privacy, which, as you might expect from the name, simply requires that the privacy loss is concentrated. So there's two parameters now, mu and tau, and we require that the expectation, so the KL divergence or the expected privacy loss is very small, it's at most mu, and moreover, when we think about it as a random variable, it's tightly concentrated around mu. In particular, the formalization is that it's no worse than a normal with expectation. The privacy loss now is no worse than a normal distribution with expectation mu and variance tau squared. Formally, we say that it's sub-Gaussian, so the distance between the privacy loss and its expectation. Once we center the privacy loss, we require that it's concentrated at least as tightly as a Gaussian. And there's a rich theory of sub-Gaussians that we draw on, and then we can prove all sorts of theorems. I won't talk about it today, it's just to sort of point out that there's different formalizations and different distance measures one could consider, and there's interesting theory or math that goes on, and interesting things you can actually show.
Sorry, I don't understand. You're fixing the two adjacent numbers, right?
Mm-hmm.
Shouldn't you have to minimize for all adjacent things? Or?
The requirement is for all, yes. Sorry. Yeah, the requirement in epsilon differential privacy, the requirement is always for all the adjacent data sets, D and D prime. In epsilon and epsilon delta differential privacy and in concentrated differential privacy. Okay, so that was a recap. and maybe a reformulation, and I hope we got some extra insights into what goes on in terms of privacy losses, and we'll come back to it. We saw yesterday that we can answer a single query using noise scaled to sensitivity. Remember, we had this nice mechanism, the Gaussian mechanism, where to answer a query Q, we just added Laplace noise scaled to the privacy that we wanted. Okay, so the bigger the privacy, the more noise, the smaller the privacy we wanted, the more noise we added.
So I wanted to ask that why you use the Laplace distribution. So which other distribution can be used?
So the distribution that I think I mentioned yesterday, the other distribution that I would like to use is a Gaussian. We generally like adding Gaussian noise, in particular in many statistical analyses. The noise you already assume is inherent is Gaussian, or it converges to a Gaussian. So we like using Gaussian noise. The problem with Gaussian noise, I mean, not a problem, it's just the way Gaussian noise is you don't have the nice, in the tails you don't have a nice behavior. So if you're unlucky and somehow you drew a Gaussian noise of large magnitude, your privacy will be very poor. And that's captured by the notion, I mean, then what you get is epsilon delta differential privacy, or concentrated differential privacy, the other notion that I talked about that also gives you, you can also get that. But Laplace is very clean, that's why we like using it. We get this perfect privacy guarantee. Okay, so what I want to talk about today is how to answer multiple queries, and even, I hope we'll get to how to answer huge query families, and tell you a little bit, or develop a little bit of a toolbox for constructing differentially private algorithms. So if I showed you how to answer a single query using the Laplace mechanism, but of course you're already very well informed and you know that differential privacy composes, so if you want to answer multiple queries, you could simply keep using, keep adding noise, answer every query with independent noise. The only thing is that the more queries you answer, the privacy losses add up and you get worse and worse privacy. So in particular, if you wanted to get epsilon privacy for answering k queries, say counting queries, you could simply scale your noise to k, add independent Laplace noise of magnitude k over epsilon to each of the queries. That gives you an epsilon 0 of epsilon over k, so epsilon over k privacy for each query answer on its own. And by the composition that we saw yesterday, we know that over the k answers, over running these k algorithms, the epsilon zeros add up, and you get epsilon differential privacy for all k answers put together. So basically, the Laplacian says they're white. So the density function says that the magnitude of getting some answer y, it's so real valued noise, and the probability of getting y proportional to e to the minus, probability of y is proportional to e to the minus magnitude of y times epsilon. And then there's some normalization. So it's sort of exponentially decreasing probability. And I'll go back a slide. It won't be very important for the talk today. I mean, the main thing I want you to know is we can answer a single query with noise, but this is what the plot looks like for Laplace with various expectations centered around various values and with various magnitudes. So it's tightly concentrated. It's not as tightly concentrated as a Gaussian. It's a little bit flatter. Okay. So if we want to answer k queries, we can simply add independent noise. The privacy losses add up. So to answer k queries, we need noise k over epsilon. Particularly, the error depends linearly on the number of queries we want to answer. For example, if what you're willing to add is square root n error tends to be something we like to add because that's usually inherent in the data anyway due to sampling effects. So if you just want to add square root of n error, you can answer square root of n queries, but no more. Okay. So that's for independent queries. We can do better for particular sets of queries. One example that I did want to bring up, even if briefly, because I think it's very cool, is histograms. So we have this data universe, okay, the universe of all possible, say, of all possible people. Suppose we're measuring incomes. This is all the possible incomes, annual incomes. And we separate the universe into disjoint bins, okay, D disjoint bins, so say income brackets, S1 up to SD. And we want to know approximately how many people in our data set fall into each bin. Okay, so those are called histogram queries. And here we have D queries in total. We want to know the number of people in each and every one of the bins. But now the observation is that for two adjacent databases, that only differ by one person's presence or absence, or only differ by one person and one person's information, only two of the answers can change. Okay, so for example, if you replace my information, my very high income, now that I'm in a corporate lab and I go, it's in a certain place, if you change me to be an academic, it goes to a different income bracket. So two of the answers have changed, right? Two of the brackets, where I previously was, there's one fewer person, and where I now am, there's one more person. Okay, so maybe this bracket decreases and that bracket increases in the data set. And this is very different from the situation where we were trying to answer a general collection, say, of D counting queries where all the answers could change by one, okay, simultaneously. Here, only two of the answers can change. And the way the way this is captured, the global sensitivity of the answer vector, if you look at the vector of answers as a vector and you measure its global L1 sensitivity, that sensitivity is only 2. For adjacent databases, that vector can only change by 2. And what this means, and there's a theorem showing this, is that we can add Laplace noise of magnitude only 2 over epsilon. So we don't need to scale the noise to the number of queries being answered, D. We can leverage the structure in this query set and add less noise, still getting epsilon differential privacy.
So it seems pretty connected to the boundary differences in quality and breakdown.
From what? To what?
Social inequalities, like the Magdian inequality.
I don't know. Does it? So, I mean, this is a very easy theorem to show. So it doesn't make use of any of those. I think what is interesting here is that we don't have an understanding. If you give me, well, actually we do have an understanding, but I think there's room to develop it. If you give me a general collection of queries and I try to understand what amount of noise do I need to add, this global sensitivity is a very crude bound. It's an upper bound. But maybe I'll be able to add much less noise, and actually there's works that think about this geometrically and try to exploit the geometry of collections of queries in order to add less noise and get better algorithms. Okay, why don't we skip over this? There's lots of other work working on specific queries. We won't get into it. What I do want to get in is revisit these composition bounds. And what we've learned so far is that if we compose, so if we want to answer many queries, we can just use composition theorems or composition bounds. And we know, for example, that the epsilons can add up. So if we have k algorithms, each of which is epsilon 0 differentially private, taken together, epsilon 0 times k differentially private. But in fact, this is just an upper bound, and I don't remember who, but someone asked that yesterday. And we can actually get something much better. So in work with Dworak and Vadhan, what we showed is that actually you get approximately behavior that grows only by root k. You can get behavior that only grows by root k, and I thought that I would actually show you that today. So in particular, that means that now if you want error root n, you can, if you're willing to add additive error approximately root n, you can now answer a linear number of queries in your data set size, which can be quite good, especially if we're talking about internet scale data sets. That can often be quite a number of queries. Mm-hmm.
How does this, how do these things change if the norm in which you measure the error changes, like L1, L2?
It's a good question. So for L2, it doesn't change much, and I don't know about the higher norms. I probably have to think about it offline. This is tight. This is tight. In fact, this is tied up to constant factors, I should say. I mean, I haven't written the constant factors, but what we proved was tied up to constant factors. And then actually in the last year, there have been 2 works showing tight bounds. So provably, exactly tight bounds up to the constant. There are some catches. In particular, some of these works show that the exact bounds can take exponential time to compute the exact bounds. So if you want to figure out how much noise to add, you might have to work exactly how much noise to add. Up to the last decimal point, you might have to work exponentially hard. But these bounds are tight up to. So if you don't care about a factor of 3, then this is as tight as you need to be. So what's a theorem? What's a theorem that I want us to show? What we show is that the composition of k algorithms, each of which is epsilon 0 differentially private on its own, is epsilon delta differentially private, where for any delta that you want, the epsilon you can get is something like root k times the log of 1 over delta times epsilon 0 plus k times epsilon 0 squared. So this, I'm focusing on this term, root k times epsilon 0, because usually when we're trying to design algorithms, this can become the dominant term. We take epsilon 0 to be something like 1 over root k, and this becomes the dominant term.
So is this where you're going to use the plus minus epsilon?
Yes. Yes.
This is for every delta. Why would you say delta is 0? Or is that not?
Because then this will grow to be infinite, and the epsilon will be
Oh,
infinite.
there's a delta there. Okay.
Yeah. Okay. So now I thought I would be brave. How do I make this board go up? There we go. So inspired by Anoop that I'll prove it on the board. Okay. So I'm actually going to do a simple case of non-adaptive compositions. So what I want to say is that I have k algorithms, A1, A2, up to AK. And I have 2 databases, adjacent databases. D and D prime. And I want to look at the privacy loss that's incurred by running all these algorithms in parallel either on D or on D prime. Okay, so in fact the theorem holds even for adaptive composition where an adversary chooses the algorithm A1, sees the outcome, then chooses the algorithm A2. It's not much more complicated to prove it that way, but let's just for fun, for simplicity, let's focus on this case. So I'm running the algorithms either on D or on D prime, and I get some outcome Z. So in particular, let's look at what happens when we run the algorithms on D. So I have, I get Z1 by running the algorithm A1 on D, and Z2 by running A2 on D, etc. And I have this vector Z of all the outcomes that I got. And remember that now what we're interested in is the ratio of probabilities, the probability that I get this outcome vector Z hat, but when I run the algorithms on D or on D prime. Okay, so I'm going to use this notation that P of Z is the probability that that you get Z when running the algorithms A1 on D, and P prime of Z, the probability when we run on D prime. And now what I'm interested in is when I run the algorithm on the algorithms on database D, I want to look at the ratio, the log ratio of the probability of Z over the probability prime of Z. Right? And hopefully what I want to show is that with all but delta probability over the coins of the algorithms running on data set D, this log ratio is bounded between epsilon and minus epsilon. Good. So let's look at this log ratio. So since we're just simply running the algorithms independently, the probability that you get the outcome Z when you're running on D is simply the product of all the probabilities when you're running the little algorithms A1 up to AK. Okay, so it's just a product, I goes from 1 to k, of what I'll call pi of zi. So this is the probability that I get outcome zi when I run the algorithm ai on data set D. And here I have pi prime, which is the same. I'm just running the algorithm D prime, on D prime. Okay, does that all make sense? So that's very nice. And that, in fact, turns out to just be the product. We can take the ratios one by one. So the product of pi divided by pi prime. And that's simply the sum of the log ratios. Okay, so let's look at what's happening here. We're basically running these k algorithms one by one. Every time we run an algorithm, the ith algorithm, we get an outcome, zi, sorry. We get an outcome zi, and we're looking at the log ratio of that outcome's probabilities when we run the algorithm on data set D or D prime. So really what we have here, thinking about these log ratios, each of these log ratios as a random variable, we have a sum of k random variables. Okay, so that's very nice. We have a sum of k random variables. Hopefully k is big. And we've already hinted or we talked about the fact that these random variables have an expectation. Okay, and hopefully their expectation is small. So we have a sum of k random variables with small expectation. Hopefully we can use concentration inequalities. So the question is, looking at each of these guys as a random variable, the ith, what is their expectation? And we also need an absolute bound on their magnitude, but that we already have. Remember, each of these algorithms on its own is epsilon zero differentially private. So we already know that each of these is bounded in magnitude. The magnitude of each of these is at most epsilon. Okay? The old composition theorem we had simply said, well, each of these is at most epsilon, so the sum is at most k epsilon. That's certainly true. What we're going to want to use now is we're going to use this worst case bound together with a much better bound on the expectation. And that'll give us behavior that looks like root k times epsilon 0. Sorry, epsilon 0. Does that make sense? So
You're going to somehow argue the expectation can't be that the ratio is always epsilon, the log ratio is always epsilon?
it can't be, and that goes back to the negative, to the fact that sometimes it's negative. So think about the example, for intuition, think about the example where we were measuring the number of people above 6 feet tall and I was in the room. It's always the case, half the time the noise is positive, but half the time it's negative. And when it's negative enough, almost always when it's negative, it looks less likely that I was in the room. So in fact, this has quite a dramatic effect. And what you can show is that the expectation is at most something like epsilon 0 squared. So looking at that bound above, the k times epsilon 0 squared is coming from the expectation. The root k times epsilon 0 is coming from an Azuma-like behavior. So we're summing k things. If we center the distribution, so we subtract epsilon 0 squared, we're summing k centered random variables, each of magnitude more or less, each with expectation 0, and if magnitude is most epsilon 0, and so Azuma will tell us that we get something like, at most, something like square root k times epsilon 0. Okay, if you ask me to, I'll show you the Azuma. Otherwise, all I'll do is show you why the expectation is at most epsilon 0 squared. Okay, so just to ease up notation, let's show this in a general way. This is actually, as we were saying before, the expectation of this quantity is just the KL divergence. So this is actually simply a statement about the KL divergence of distributions that have a certain property that they inherit from differential privacy. So in particular, let's take the x and y to be random variables, where for any outcome z, the log of the probability of z according to x and the probability of z according to y is at most epsilon. Okay, so think of this as the distribution of running the algorithm on data set D. This is the distribution running on D prime. And this is the guarantee that we get from epsilon differential privacy. Okay? So as we were saying, what we want to bound is the KL divergence from x to y, which is simply the expectation over z drawn from x of this log ratio. Okay, that's what we want to bound. And so let's do it. So the only non-trivial property I'm going to use is non-negativity of KL divergence. This is something you get, I assume many of you know, this is something you get from the log sum inequality. All I'm using is that the KL divergence from x to y is bounded by the divergence from x to y plus the divergence from y to x, because this quantity is non-negative. Okay, KL divergence is always non-negative. That's this quantity, and let's spell out what that is. That's simply the sum over all z of x of z okay, plus sign. And we're going to show that this is at most something like epsilon 0 squared. This sum is at most something like epsilon 0 squared.
So you don't assume any lower bound on y of z, for example. It's going to get small.
Yes, but x and y are distributions. So y and the y's always sum up to 1, and they're always non-negative. Yes.
I'm asking because otherwise you would be opposite. Because x of z and y of z are close to each other. So then you could give log of log. Log of lambda is something small.
Perhaps, but I'm also sure there's many ways to prove this. But this is the simplest one I know. And maybe we'll learn today that it's related to something well known in information theory, which would make me very happy. Okay, now I'm just going to do some standard manipulations or some simple manipulations. So what I'm going to do is basically I want to get rid of this term. So I'm going to subtract here or maybe add the log of y of z over x of z. So I'm adding that here, and I'll need to subtract it here. So this quantity log of y of z over x of z, I need to subtract it in the second term. Okay, so that's very nice. I added and subtracted, this this sum is equal to 0. Okay, so we can just cross this out. And here I have y of z minus x of z times the log of y of z over x of z, and that certainly is at most the sum over all z's of the magnitude of y of z minus x of z. So I'm replacing this with this can be positive or negative, but I'm replacing it with a magnitude, and this I'm replacing by the maximal value of the log ratio, which is simply epsilon. Okay, so I'm summing over all z the absolute value of the difference of the probability of z according to y of x, sum multiplied by epsilon. So that's very nice. I can take the epsilon out. And now notice what I have here. I have y of z minus x of z. That also can't be too big. In particular, this is at most, remember y of z and x of z are at most an e to the epsilon apart from each other, an e to the epsilon multiplicative factor apart. So this is at most e to the epsilon minus 1 times the minimum between y of z and x of z. Again, using this multiplicative bound. So I take the e to the epsilon out. I have to epsilon times e to the epsilon minus 1 times the sum of the minimum between two probabilities certainly this sum, even if I remove the minimum and just sum over y or over x, this is exactly 1. So the minimum is at most 1. And so the bound I get is exactly epsilon times e to the epsilon minus 1, which for small epsilon is about epsilon squared. Good, so yes, I can lift the one behind up. How's this? Good. So yeah, it's very nice. I mean, looking at these privacy losses as random variables, and I think this came up, I'm happy that it, we were sort of leading up to it. We're able to use the fact, and this is heavily using the fact that the expectation is actually much smaller than the worst case behavior, always. And that actually gained us quite a lot. As we'll see, it'll be important in, it'll sort of power more and more sophisticated algorithms that we can use. So this really is an important fact about differential privacy, not just in general, but also in the design of specific algorithms.
Can you combine epsilon delta and
Yes, and what happens is that the deltas add up. Again, it's a non-trivial proof. So the way you actually structure this is you show an equivalent formalization that says that when you have epsilon delta, you're actually at delta L1 statistical distance from really being epsilon private. And so what you do is you pay that statistical distance, you move to something that's really epsilon private, you activate the composition theorem, and then in the end you come back with that delta distance. So the deltas also add up. And I used the Zuma's inequality because really here I was doing, I could have used a stronger inequality, but in the full proof of this theorem we want adaptive composition, and then really what we have in the privacy loss is a martingale. And we use the Zuma's inequality to bound the magnitude of that.
Do you have examples showing this is tight?
Yeah, there are examples showing this is tight. So here I showed something like epsilon squared. You might immediately object and say, well, you paid a lot here, right? Like I paid a factor of 2 in bounding the KL divergence from x to 1 by the sum of these KL divergences, right? Like why do I need to also pay for the KL divergence from y to x? I added something that was bigger than 0, but it could be much bigger than 0. So in particular, there's a more complicated proof that shows epsilon squared over 2. And then there are slightly tighter bounds that are exactly tight for specific mechanisms.
Does that the field of some reverse Pinsker inequality?
Sorry?
Does that the field of some type of reverse Pinsker inequality?
Wonderful. Yeah, so I'll ask you about that. Okay, so that tells us that we can answer n queries with error root n, just by straightforward composition bounds. And it turns out that that also is tight. I mean, you might think about answering n queries in all sorts of different ways, not just by adding independent noise and composing mechanisms, but you cannot answer n counting queries with less than square root n error. This is early work that predated even the definition or the formalization of differential privacy. If you answer n count, there are examples of n counting queries that we can construct where if you answer them with less than root n noise, you can essentially reconstruct the entire database from the answers. So you get very strong privacy violations. You can't add error less than root n if you're answering n queries. But it does lead us, okay, we can't do better than root n for n queries, but root n usually is a pretty good error to have because it's already inherent in the data. The question is how far can we push this root n error? So in particular, the question is, can we achieve root n error for much more than n queries? Okay, can we achieve it for n squared, n to the 3, what about exponential in n? And notice this is sort of, I think this is a fundamental question, right? That has nothing to do with privacy. It's a question about, well, that has nothing to do specifically with differential privacy. Is there any reasonable notion of privacy under which we can release, say, an exponential number of statistics without compromising the entire database? That's a good question to ask. We don't know the answer to that. I'll be even more ambitious, and I'll ask, can we answer an exponential number of queries with differential privacy, with a strong notion of privacy protection? And we'll see that the answer is yes. You can answer huge numbers of queries with very small error that essentially approaches root n, and with differential privacy. Good. So I'll try to show you the first of these mechanisms today, and I'll spill over tomorrow to show you the second one. So that's going to be the next thing we do, huge numbers of queries. In order to do that, I need to introduce another tool, the exponential mechanism, which was invented by McSherry and Talwar. And their motivation was, they weren't trying to answer queries. They were just saying that sometimes adding noise doesn't make sense. For example, if we have a query where the answer isn't a number, okay, then it's not clear what adding noise means. Their motivation was auction design, where we have outcomes and we want to choose an outcome. And they had this observation that differential privacy has this connection to game theory. And there's been a lot of follow-up work on that. In particular, it implies some approximate notion of truthfulness. So what is the exponential mechanism? I'll just give you an example. And the example, we're after lunch, but maybe we can use it tomorrow. So we have n individuals, and we have k options for lunch, options 1 to k, and each individual likes or dislikes each option. Okay, so that's the setting. What we want is to output a lunch option that many like in a differentially private way. So we want a differentially private algorithm that will output a lunch option that many of the people like. The mechanism that we'll use is to output each option j. We'll simply construct by brute force a distribution over the k lunch options. And we'll output each option j with probability that's proportional to e to the epsilon times the number of people who like j. Okay? So this is the probability I want. In order to make it a distribution, I'll have to normalize. So we output j with probability e to the epsilon times the number of people who like j, divided by the scores that were given to all the other lunch options. So in particular, the probability of outputting a particular lunch option grows exponentially with a number of people who like it. That's a nice property, and that's the algorithm that I want to use, and I'll claim that that's a differentially private algorithm. We didn't really add noise, we didn't count, we simply constructed this distribution, and this distribution, as we constructed it, will be differentially private. Okay, so why is that? For any two adjacent data sets that only differ in one person's likes or dislikes, for any option j, the number of people who like j can only change by 1. Right? A person can only increase or decrease the number of people who like j by 1. So if we look at the probability of outcome j, what we want to show is that it differs by a small ratio between database D and database D prime. So going from D to D prime, the numerator can only change by an e to the epsilon factor, because L of j can only increase or decrease by 1. And similarly, for every summand in the denominator, it can only increase by an e to the epsilon factor. It can only increase or decrease by an e to the epsilon factor. So this whole sum can only increase or decrease by an e to the epsilon factor. So in the worst case, what happens is that the numerator increases by an e to the epsilon factor. The denominator decreases by an e to the epsilon factor. But we still get that in total, this total probability only changes by an e to the 2 epsilon factor. So that gives us 2 epsilon differential privacy. And now we can have lunch. I claim that it's also not such a bad algorithm for choosing how to have lunch, because we have this exponential decrease in the probability when many people don't like a lunch option. So in particular, if a lot more people like option J2 than the number of people who like option J1, the probability of J1 is e to the epsilon d times smaller than that of J2. Okay, so the probability will be much, much smaller. In particular, for any option that is much smaller than the optimum, than the one that the most people like, so if j is smaller than the best option by at least log k plus b over epsilon, then the probability that we output j is at most 1 over k times e to the b. That's simple by the construction of the algorithm. And so if we take a union bound, if we look at the best option, we take a union bound over all the options that are suboptimal, that differ by at least log k plus b from it, the probability that our answer is much smaller than the best option is exponentially small in b. Okay, so we're within log k over epsilon of the optimum. where B is kind of our extra error term, whatever error probability you want. Okay, is that pretty clear? So
Is there a way of saying that that's the best solution? Like,
it often isn't. It often isn't. So there are two problems with this algorithm. This is a wonderful algorithm. There are two problems with it. One problem is computational, which you have to construct this brute force distribution, and if there are many options, that can take quite a lot of time. You could compare this, for example, with an algorithm that tries to add noise to the number of people who like every option and then pick the maximal noisy answer. And that algorithm can often do better up to constant factors. So the algorithm just computes all the L of J, adds noise, independent noise to each of them of a certain magnitude. You have to figure out what magnitude you need, and then picks the best one. Picks the max. So it's an alternative algorithm that I think outperforms this by a constant factor. So
in terms of
the guaranteed difference between the answer and the optimum. Yeah. So let me, actually, I think that's insightful. In many cases, you can, in some cases, you can sort of say that this is a meta algorithm. And given any algorithm, you can sort of transform it to have this form. There are these kinds of transformations that take this sort of a meta optimal algorithm, but they do lose something in the conversion. They do usually lose something in the conversion, and they lose a lot of computational efficiency. So it's a sort of a central important algorithm, but we usually use it to show general feasibility results rather than tight results. Okay, so in the little time that I have left, I want to show you how to answer, I promised you I would show you how to answer exponential sets of queries, and I want to show you how to do that. So this is an algorithm due to Blum, Liggett, and Roth that shows how to answer any set of counting queries. So you specify a set of counting queries, and it produces answers to all of these queries simultaneously, where the error, the maximal error over any of the queries, is about n to the 2/3 times log the number of queries. Okay, so not quite the square root n that I promised you, but pretty close. In particular, this is the first example we had that could answer really very rich query families. In particular, the number of queries can be much, much bigger. So you can take Q to be something like 2 to the 0.1 times n. Answer a huge family of queries, and you still get n to the whatever 0.68 error, which is sublinear in particular. That's quite good. Another interesting fact is that this algorithm actually outputs a synthetic database. So it outputs a complete database that is not the input database, but is close. The answers on the synthetic database and the original database are about the same for all the queries in this family. It's an interesting artifact of the algorithm, and there's been a lot of work on that, which I won't get into. But I did think I'd mention it. So what's the algorithm? We're given an input database. It's of size n, and we're given this query set Q. And now what we're going to do is we're simply going to output. I told you the output is going to be a database, and it's going to be a small database of size m. M is smaller than n. And we're simply going to pick it by a brute. We're going to construct some distribution by brute force. Okay, so we're going to pick every database, for every database f of size m, for every possible database, we're going to pick it with probability e to the minus epsilon times the distance of f from d. Okay, so we're enumerating over all the databases of size m, an exponential number of databases. For each of them, we're assigning a certain probability that depends on its distance, and then we're going to sample from this distribution and output our sample. So a very simple algorithm. The distance here that I'm talking about, so the distance between the database f and d, is just the maximum over all the queries, the maximal distance over all the queries of the query answer on f and on d. So for this algorithm, actually, the proof of privacy is going to be trivial. It's going to be very simple to the exponential mechanism that I showed you before. The interesting thing is going to be, well, do we have any utility? I mean, are we just outputting junk? Or are we usually outputting databases that have nothing to do with the original database? And the intuition is that no. And similar to how to what happened when we were picking lunch, The intuition is that databases that are far, that get a bad score, that are distant from the input database, have their probability really dramatically decreased. And so it's going to be very unlikely that we output any of them. Yeah, so this is a terrible, this algorithm has terrible running time, and we'll get to it. And in fact, the running time, there is work showing, or we were able to show that the running time is tight if you want to output a synthetic database. That's kind of an artifact of synthetic data sets. Okay.
So is this like kind of like adding noise to every bit location and then like independently and then is that
It's not. So the important thing is that the noises here are correlated. So
there's a query space.
yeah. So this is the maximum over all queries. And in fact, you can't, so I should have said it, but you can't simply keep adding independent noise to queries and hope for privacy. And the reason is that I could mask, you could be answering queries that look like they're different, but really I'm asking you the same query over and over again. You just can't tell.
Well, what I was thinking about was that you were adding noise to the records, because that's sort of like, I mean, if the measured distance is like somehow the Hamming distance and not this.
No, so,
Like that, but
yeah. So, it can't, yeah, it's not the Hamming distance, it's query distance. Yeah. So let's see the proof of privacy, and I think that'll make it clear. So why is this a private algorithm? So for two adjacent data sets, D and D prime, that we might have at input, for any candidate output that we might want to produce, I claim that the difference between the distance of f from D and the distance of f from D prime is at most 1. This is because the answer to every query on D or on D prime can only differ by 1, and so the distance of the maximal query, the distance according to the maximal query between D and F and between D prime and F can only vary by 1. Okay, so just by the low sensitivity of these counting queries, we get that this distance itself doesn't change by much when we go from D to D prime.
Excuse me, I want to say something simple. Assume that there are no databases at all size less than m.
Great question. Great question. So there are data sets of size m. So m is the number of records. Right? So I can certainly construct a database of size m. In particular, I can sample a data set of size m randomly from the data set D.
I see.
Yeah? So there are data sets of size m, and there are even data sets of size m that are close to the input data set. I won't want to release those because that's bad for privacy, but they do exist. But let's separate the proof. What you're asking is for utility. Right? How can it be that this algorithm actually outputs something helpful? But for now, we'll just do privacy. So when we go from D or D, when we go from D to D prime, this distance measure can only change by 1. The probability of a candidate data set by F, according to when we run the algorithm on D, is e to the minus epsilon times the distance between F of D and D divided by the normalization, which is the sum over all data sets of their sort of score. So the score of F divided by the sum of all the scores of all the data sets. And when you look at the probability of F by D prime, as it was in the lunch example, well, the numerator can only change by e to the epsilon, because this distance can only change by 1. And the denominator, every summand can only change by e to the epsilon, or e to the minus epsilon, because again, the distance can only change by 1. And so the probability of F can only change by e to the 2 epsilon.
So the thing you use about the distance measure is this line.
Yes, that's all I need. And that's sort of the generality of if you think about the exponential mechanism as a way of picking from a set of possibilities, when you have a score function, what you need for privacy, the only thing you need is that this score function has low sensitivity. So for every possible outcome, we assign a score. Here the score is sort of its distance from the input. And the score is insensitive. Right? The score of any possible outcome only differs by 1 on adjacent data sets, and that automatically gives you privacy. Okay, and as I said, the utility is a little bit harder to show, so
Sorry. What if
absolutely.
you deleted each record with probability
So that would be great for utility. In particular, you could sample.
not be private?
No, because even if you only release one of the records at random, that's not private because you might release mine.
No. So, sorry. Are you releasing the whole database? Is that the main thing?
I'm releasing all of F. I'm releasing F.
So what you suggested though is a bulby is to do the queries. So you could just cook up a query that asks for a particular individual.
Okay.
Cook up a database that has the individual in there. And then if you subsample.
No, subsampling is actually a good idea for utility. The problem is privacy.
Privacy.
Yeah.
So the problem is that there are queries that would mess that up.
So I guess what I'm missing is in this proof, the queries don't show up at all, and the only feature of the distance that's used is this line, which seems to be satisfied by.
No, so we're using the fact that the answer to any query can only change by 1. So all we're using is low sensitivity of the queries.
The distance is a function of the queries.
Yeah, the distance is the max over all queries of the change in the query value between F and D. So the distance does depend on the query. What I'm using about the distance is that it has low sensitivity, and that's directly inherited from the low sensitivity of the queries.
But you should go on.
So let's quickly maybe just go over it, just review it. We have a couple more lines and then I'll be done. So I'm picking any possible database F with the probability that is exponentially related to its distance. That's sort of the score it gets. And then I'm normalizing according to this score. I release the entire database F. Okay, so I sample it according to this funky distribution that I cooked up, and then I release that entire data set F. The distance is the maximum over all queries of the different distance of the answer, the query value on F and of D. Now all I'm using for privacy is that this distance can't change by much when I go from D to D prime. So the distance of any possible candidates, think of F as your lunch options, and the distance of any candidate, or the score of any candidate, will only change by 1 when I go from D to D prime. So this whole probability distribution won't change by much. For every singleton in the probability distribution, it'll only change by e to the 2 epsilon. Yes. Okay. So why does this algorithm have small error? So fix any desired additive error that we want, and let's look at data sets of this size, n to the n over alpha squared times log q. So what I want to say is once we fix this size, so this size is going to be the smaller error we want, the bigger the m that we'll need to deal with. Okay? And what I want to say is that if we pick m to be this large enough, there exists some f star, some database of size m, whose distance from the real data set, from the input, is at most alpha. So that's going to your question about why there even exists a small data set that is good. And this is true simply because of sampling. So by sampling, we know that if we pick m records at random from the original data set, and we're talking about counting queries, sampling bounds will tell us that we'll have at most alpha error on all the queries. So for each query individually, we need n over alpha squared samples. And in order to have alpha error at most over q queries, we need to multiply the number of samples by log q and take a union bound. Okay, so if we take m to be large enough, we're guaranteed that there exists a really good f star. Of course, we don't want to output that f star. All I want to claim is that it exists. Okay, so the probability of its score is going to be really high. It's e to the minus epsilon times alpha for this small error alpha that we wanted. Okay, so there's one good data set, and I'm going to output it with pretty good probability, or it gets a pretty good score. On the other hand, for any bad data set, anything that's at least 2 alpha or farther away, its probability is going to be much smaller, e to the minus 2 epsilon times alpha. So there is a good data set. I just argued its existence. And on the other hand, all the data sets that are far, that are much worse than it, get very, very small probability. In particular, this probability, I can just union bound over all the bad data sets, and the probability that this algorithm outputs any bad data set is proportional to is at most, by a union bound, the number of data sets times the probability of each of them that is bad. That's a simple union bound, so that's my probability of outputting a bad data set. Probability of outputting a good data set is at least this, because there's at least one data set that's good and gets this score. And by picking alpha, or the smallest alpha, the smallest error for which this term wins over this term, is n to the 2/3 times log q. You can check the calculation. But by picking this alpha, or I still get that the probability of the good data set, even the single good data set that I claimed existed, is bigger than the sum of all the probabilities of the bad data sets. Because I can sample from the real data set, the real input data set. I can take a sample of size m, and by sampling bounds, we know that when you sample, usually the answers are very close. We're talking about counting queries, so when you sample by sampling effects, the answer is very close to the original input. And so by taking a large enough sample with high probability, the answers are going to be good on all the queries. And there's something confusing about this theorem, because I don't want to output this data set, right? But you sort of have to divorce your view of privacy and utility. We prove privacy, we don't have to worry about it anymore. And here we're just showing utility. And utility uses the existence of a good data set that isn't private, but who cares? We already proved privacy. Okay, and as was pointed out, the running time is really, really tremendously bad. So it's not just an exponential, it's sort of a double exponential. So it's the size of the universe to some polynomial in n. So that's the algorithm I showed you. It was an offline algorithm, so I needed to know the query set. I needed to know all the queries. Then I cooked up this distribution by brute force. So it's an offline algorithm, but it did get interesting error even for huge families of queries. It had a catch in the running time. And what I'll show you tomorrow is, I guess, it's still the state of the art and known to be tight by some measures, multiplicative weights algorithm that is online. So it'll get better error bounds, better running time, and it doesn't need to know all the queries in advance. You can simply ask it queries one by one, and it'll give you answers one by one with error that just grows as root n. That's what I promised you. And the running time is going to be polynomial, but I do want to emphasize it's still polynomial in the size of the data universe. So we'll talk about that tomorrow.
So your m is fixed. So
yes.
The parameter computed from m, right?
Yes.
And what's the size of m? Can you show once more? It's square root of m, something like that?
No, it's so you also fix your alpha. So here we'll have alpha equal, think of alpha as equal to n to the 2/3, more or less. And so m is also something like n to the 2/3.
So it might be greater than m.
No. So alpha is a large number. It's n to the 2/3. N divided by alpha is n to the third. This is something, again, like n to the 2/3. So m is something like n to the 2/3.
You just want to know how large is your database, right? So the number of elements. So then m is much less than n.
Yes.
How can you obtain a correct answer then?
So we know this, so I'm giving something up, right? If I'm willing to get error, so if you want, for example, if you want to know the number of zeros, or the number of bits that are, you have a database of bits and n bits, and you want to know the number of zeros and ones, if you're willing for an approximate answer that's only has n to the 2/3 accuracy, that if you're willing to get an n to the 2/3 additive approximation, you can do it by simply sampling n to the 2/3 of the bits. So you don't have to read all the bits.
So your ultimate answer is not just the query applied to the database.
No.
The sample.
Yes. Yes. So here I'm sampling. I mean, in the end, I'm just picking a database and outputting in it. That'll be my answer. But here, in order to argue the existence of this good F star, I'm sampling from the original data set.
No, I mean, when you sample your database of size m, you do after that, after you have already picked your database,
Yes.
you do not apply to Q the query to database, right?
I do in the algorithm, but in the analysis.
No, in the algorithm. What do you do?
So in the
You want to know how many entries.
So the algorithm is very simple, right? I look at every possible data set of size m. The size m is fixed. We know what it is. So it's n to the 2/3. So I have my input database of size n, and I have my subsample database of size n to the 2/3. Or, sorry, a candidate, it's not subsample. I have a candidate data set of size n to the 2/3. And now I look on each of the queries, and I see how different the answer according to F is from the answer according to the original database. And I normalize these answers, I scale them.
Normalize, it's multiplied by the ratio of
Yes,
M and F.
yes. And then I look at the query on which they're farthest apart, and that's the distance.
So Could you hope to get like a Markov chain with samples from these things faster?
Yeah, really good question. So so complicated answer. In general, the answer is no. Unless, if you believe that cryptography exists, then the answer is no. So we can actually use cryptography to cook up strange query families where we show that sampling from these distributions is hard, is computationally hard. However, for specific query families, it may very well be yes, and I think that's a great direction for research. I don't know of an example that actually works that way. But you'd have to leverage some structure in the query family. Okay, thanks.